Okay, so third question was interesting. It said you are given few cities, let's say 1, 2, 3, and 4, and then 2 is connected to 4. So you have 7, 9, 5, and 6. So we are kind of given a graph, which is weighted graph. Our focus is to tell what is the minimum edge weight on a path from 1 to 4. It was 1 to n if graph has n vertices. So 1 to n we have to find the minimum edge. So here if you are going from 1 to 4, what is the minimum edge we encounter? Yeah, we encounter 5. But let's say if I make this as 2. Now from 1 to 5 if you are going, what is the minimum path you will encounter? Or minimum edge you will encounter? Yeah, so ultimately this problem they made it in such a way that if you are going from 1 to 4, they are saying you can go from 1 to 2, 2 to 3, you can come back from 3 to 2, and then you can go back to 4. In this path, if you look at what is the minimum edge that we have come across, that is 2, and answer for this is going to be 2. So in nutshell, can we say if there is one connected component, if all the vertices are connected, all we are trying to find out is what is the minimum edge weight. So all we have to do is we just have to find minimum edge weight in connected component. Yeah. So this problem can be solved in multiple ways. When I did it in the contest, I used the concept of union find, which is which doesn't require much knowledge of graph, which is just a clever use of arrays. So before we discuss union find, just wanted to ask, how many of you are already aware of this data structure? Union find disjoint set. UFDS we call it. Okay, 2 people. Yeah, that's fine. We will talk about that. It is just array and little clever use of array. So array plus recursion is what is the concept required. Uh, Shashank, how did you solve this problem during the contest?
I implemented a Dijkstra's approach,
Okay,
and in the heap, while we calculated, I just kept track of the shortest path.
minimum edge that you were inserting.
Yeah,
Path or edge? Just the minimum edge.
just the edge, just the edge.
Minimum edge. Okay. Srinivas, what about you? What approach did you use?
Sir, I did not type yes for like solving this question. I typed the yes before.
Okay, sure, no problem. Did anyone else solve this problem during the contest?
Uh, yes, sir, I did. Path.
Yeah, Path. Which approach?
So, sir, I basically used hash set, sir.
Okay.
Uh, so I code in Java. So
Mm-hmm.
what I did was I took a set, I put it the value of 1 and n in the set.
Okay.
Uh, then initially what I thought was if I would just make a double for loop, since the second loop will only go for like 3 times, right? Since
Uh-huh.
there are only 3 values inside the second array, like inside of the array.
Right.
So at first I thought if I would just add the values and
Mm-hmm.
I'll check if the value is like present in my hash set,
Mm-hmm.
then I'll add the value to an array.
Mm-hmm.
Then the distance of that part will be added to the array,
Okay.
and then I would just sort the array and get the minimum value out of that.
Okay.
but that kind of raised a problem of like when like the few of the elements were a bit disjoint from the graph,
Mm-hmm.
they were also getting inputted.
Okay.
So I changed a bit in the approach. I then created two different for loops.
Mm-hmm.
Both of them were similar. Just for in one for loop, I just iterated through the throughout all the arrays,
Mm-hmm.
and I like continuously took the values till the set size was constant.
Okay.
And after the set size became constant, I went on and I did the same process. I added the distance and then I sorted it and got the minimum value.
Okay.
Yeah, it was a bit lengthy process, sir, but I submitted and it
You.
worked. So
Okay. Fair. Okay. So yeah, Shashank used Dijkstra's algorithm, and Parth says he used some form of set to kind of solve the problem. Anyone else? Or anyone else who had some idea, probably like that you did not conclude that or uh, solve the problem? Because this third and fourth problem are mainly about talking about in what direction your mind runs and how do you essentially conclude that idea that I can apply this to solve the problem. Okay, no worries. Then we will proceed with the first concept. And union find is very useful concept. It is easy. Like once we implement, once we understand the idea, we can create a class of it and keep it ready for the future contest with us. Okay, so let's first explore this idea of union find here. See, idea is simple. For each vertex, we will remember its parent. We'll form a parent array. So we will use two notions, parent and root notion. So first of all, in this array, we have four elements, 1, 2, 3, 4. We will take the array of size 5. We will use on index 1, 2, 3, 4. Initially, we will say 1 is its own parent, 2 is its own parent, 3 is its own parent, 4 is its own parent. So initially, we create an array of size n and make everyone their own parent. Visualization wise, you will visualize it like this. 1 is a node, 2 is a node, 3 is a node, 4 is a node in the graph, and they are not connected to anyone. So that means they are independent. That's why we call it they are disjoint sets for now. Okay, so we have four disjoint sets available. Next, we are given edge queries. We are told first edge was 1 and 2 are connected and the weight between them is 2. Now, when we say 1 and 2 are joined together, there is an edge between them. What we start doing is we have to connect 1 and 2. This is the edge we are inserting. Let me call this is edge U to V with weight W. So what we will decide is we will decide to make one of them as parent. You tell me, what do you want? Either you will become V's parent or we will become U's parent. We can go with any notion. So let's fix that here. If I'm joining 1 and 2, I have to maintain the parent array. So I need to make either one parent of 2. I can go with either this approach, 3 and 4 are still separate, or I can go with make 2 as parent of 1 and have 3, 4 separately. We can go with any of the idea. Just tell me, what would you prefer? Okay, 1, 2. 1 is parent of 2, so let's go with that. So 1 is a parent of 2. We have joined them here, and 3 and 4 are separate. So now if I ask you, in this graph so far with one edge insertion, how many components are you seeing? How many different parts of the graph are you seeing? 3 parts. Srinivas, 1, 2 is together one part, 3 is separate, 4 is separate. Okay, so if you see, we can also count components. Initially, there were 4 components, and after one join, it became 3 components. Okay, next edge that we saw in the example was, next edge says 1 and 3 are connected, weight is 4. For now, I'm just keeping the weights aside. We will bring them in. Now, if you go with this idea, you made 1 as parent of 2. Now, 1 and 3 edge is coming. So, who will become the parent now? For 1 and 3 edge, according to our idea, we were making U the parent of V. So 1 will become the parent of V, 3 also. So 1, 2, and 3. Now 4 is still separate. So now if you see, the components became 2. Next edge that we got was 3, 4, 7. 3, 4, and 7. So for 3, who is the parent? In this, if you see, who is the parent of 3? Parent is 1. Who is parent of 4? Parent of 4. Parent of 4 is 4 itself. So what we have to do, earlier we were talking about we will join u and v, but actually what we do, we join root of u as parent of root of v. This is what idea you will keep in mind. Okay, so we are joining 3 and 4 doesn't mean that I will put 4 here. No, we will not do that. We will, when we are joining them, we will use the notion of their roots. So we'll find out root of 3 is 1. Root of 4 is 4. So we will join the roots of both the parts. So that means our joining will happen on 1 and 4, not on 3 and 4. 1, 3, 4, 2. So this is what it becomes, and we eventually come down to one component. Okay, so ultimately we used a join operation. So I'm just writing a small thing here. When you are inserting an edge, when you are saying insert edge from U to V with a weight W, for now we did not use weight. What we said is we find root of U. We will write that function separately. We'll make that separately. We will find the root of U. Then we will find root of V. We'll say find root of V. Rather than joining U and V, what we will say parent of RV, because we were making U as a parent. So parent of RV is equal to RU. Are we clear with these 3 lines that I have written here? Is this making sense? Yes. Are we clear with what it says here? Only
Can you explain once more, sir?
Sure. So let's try to kind of take another example. Let's say you had 1, 2, 3, 4, 5. If I say join 1 and 3, after this we say join 1 and 3. Find out who is the root of 1. We are maintaining a parent array, but you answer me who is the root of 1. Yeah, root of 1 is 1. Basically, a parent who is its own parent. 1 is its own parent, so 1 is the root. Okay, so when you are joining 1 and 3, find root of 1, find root of 3, and connect them. So you are going to make it as once 1 becomes parent of 3, and this is 2, 4, and 5. And parent array will get modified. 3's parent will be updated to 1. Are we good so far?
Yes, sir.
Now I say, let's join 3 and 2. So what change will happen? We are connecting 3 and 2.
3's parent is 1, sir. So
Yeah,
1, 2,
3's
3.
parent is 1, but don't stop at the parent. Who is root of 3? 3's parent is 1. Who is parent of 1?
1, sir.
1 itself. So 3's root is 1. Is that correct? And who is 2's root? Who is root of 2? Yeah, 2 is his
2,
own
sir.
parent. 2. So ultimately the change that will happen by inserting 3, 2 will be, it will now become 1, 3, and 2. So this is what our structure became. That means parent array will get modified. 2's parent will become 1. 3's parent is also 1. This is the modification happening to parent array. Okay. Now let's say we join 4 and 5. What will change if you are joining 4 and 5? 1 to 3 is as it is. So ultimately 4 will become parent of 5. Are we clear with this? Yeah. Now tell me what will happen if we join 3 and 5. If you're joining 3 and 5, what will happen? So first of all, for joining, tell me who is the root of 3. Can you tell me who is the root of 3?
It's 1, sir.
Root of 3 is 1. Yeah, so we found out the root of 3. Who is root of 5?
4, sir.
4.
Root of 5 is 4. So what I was saying, when you are joining two vertices, you don't join those vertices, you join their roots. So first one, root of 3 will become parent of 4. So ultimately now the joining will happen. It is 1, 2, 3, and 1 becomes parent of 4. Basically, a parent relationship you insert among the root of two nodes. Are we clear with this part? Yeah. Now you look back at 3 lines that I wrote. These were the 3 lines, and now connect them to what we discussed just now. Is this making sense now? Yeah, and who asked this question to explain again?
Sir, I did.
Yeah, so Parth, is it clear now?
Yes, sir.
Okay. So this is called our union operation. The data structure we are talking about is union find. So we understood how union is performed. Union is like insertion or joining two components together. So you can also call this function rather than insert, call it we are doing union of two vertices. Okay. So union operation is clear, and we are understanding who becomes the ultimate root. Along with the root, for every root, we will also start remembering what is the minimum edge weight of all the vertices connected to it. Okay. So that means when our first edge inserted here was 1, 2, and 2. 1 and 2 were connected, and between 1 and 2 the edge weight was 2. So I am also going to remember for 1 at root level I will remember what is the minimum edge weight. And this I will take another array, let's say minimum edge weight. So when 1 became the root, ultimately 1's value will be 2. So we are very clear that for this component 2 is the minimum edge. Next was we connected 1 and 3, and 4 was the edge weight between them. So 1 was becoming the root, but 1's answer is already 2. We are getting another edge of 4. Should we update this answer? We want to remember the minimum weight edge which is connected to 1. 1 and 2 are connected by edge weight 2. Now we are getting another edge 4. We don't want to update this answer. So this answer we will let it be 2. Next, you are joining 3 and 4. When you are joining 3 and 4, between them the edge weight is 7. So when we connected 3 and 4, wait, I think I am processing different queries. 1, 3 was connected. Okay, 1, 3. 1, 3 is 4, which is done, joined. Now when we are connecting 3 and 4, 7 is edge weight coming. At 1's level, the edge weight was still 2. Now when 7 is coming, it will still remain 2. So 1 is the ultimate root, its edge, its minimum edge connected to it is 2. Yeah. So ultimately, along with union operation, when we are updating parent of RV, we can also update minimum weight of RV is equal to, I'm adding one more line, minimum weight of RV is equal to min of W comma, whatever was minimum weight of are we earlier? Is that correct? Is this idea making sense? Okay. Yeah. So union we understood. Now the question is, how do you do the second operation, find? Find operation is ultimately when you say u and v, all you have to tell is whether u and v are connected or not connected. How can you tell two vertices are connected or not? Let's say our visualization became something like this: 3, 4, 5, 6. After edges insertion so far, this is what our graph has become. Now, if I ask you, are 4 and 7 connected? What do you say from this graph? Are they connected? Answer is no. If you talk about the parent array in parallel, parent of 1 will be 1, parent of 2 is 1, parent of 3 is 2, parent of 4 is 2, parent of 5 is 5 itself, parent of 6 is 5, and parent of 7 is also 5. This will be our parent array for these edge insertions so far. And we also talked about having a find root function. If I ask you, find root of 4, what will be the root of 4? In this graph, what is root of 4? It is 1. And how do you get from parent array? You go to 4, find its parent. You go to 2, find its parent. Now parent and value are same. So ultimately, from array itself, you can find the root of any node. So we are doing all these operations on array. So root of 4 is 1. What is the root of 7? Yes, what is root of 7? It is 5. So you will go to 7, find its parent. From here, if you see parent and this are equal, so root of 7 is 5. If parents are different, if roots are different, we can easily declare they are not connected. Is that true? Right? Okay. So now this is the crux of union find. So if you really see, for union find data structure, first thing we do is take array of size n plus 1 and name this array as, what were we maintaining in this array? Call it parent, not root. Srinivas, we were just remembering parents. Using parent array, we will find roots. Okay. Second step, for all I is equal to 1 to n, for each, sorry. For I is equal to 1 to n, we are going to initialize parent array. Initially, we will say parent of everyone is, parent of I is equal to, what did we do initially? Parent of I is equal to I, yeah. So everyone is considered to be its own parent. Third thing, we need a function which can do the insertion, which we call as union function. So we have to write union function. Before union function, let's write a find root function. How do you find the root using parent array? If I give you a vertex u, how can you find its root? Can I simply say, if u is equal to parent of u, we are very clear who the answer is. If for any vertex, it is its own parent, what we will return? Who is the root of I? Initially, if your parent array is 1 is 1's parent, 2 is 2's parent, 3 is 3's parent. Visually, it will be 1, 2, and 3. Who is the root of 1? 1 only. So that means if index is equal to its value, can we simply say that index itself is the root? Yes, otherwise we make a recursive call, we say return, we make a recursive call, find root of parent of, recursion will take care of rest of the things. To understand this scenario, if you see 1, 2 and 3, imagine if this was the case, parent array would have been 1 is 1's parent, 2 is having 1 as parent, 3 is having 2 as parent. Now if you want to find the root of 3, you are asking who is 3's parent, it is 2. Recursively you are saying, hey, find the parent of 2. You come to this. Now you see the parent of 2 is 1. We are saying, hey, find the parent of 1. When we come to 1, we hit this condition. Hey, 1 is its own parent, so 1 must be the root. So 1 returns himself, 1 returns himself. That's how we get the root. Are we clear with find root function on this array? Yes. Okay. Fourth thing, using find root, we will write union and find functions. So we have to do union. That means we have to join two vertices. Int u, comma, int v. How did we write union function earlier? What did we discuss? How will you join two vertices? Yeah, you have to find roots, not parent. Root of u using find root function. You will find root of v using find root function. You found the roots of both. All we have to do now is to join them. How will we join? Parent of rv is equal to ru. Is that correct? Yeah. And now last function remaining is just to know whether two nodes are connected or not. This is the basic of union find. So fifth function is bool. This is called find function. You just have to find out whether u and v are connected. This will be one liner function, return find root of u double equals find root of v. Are we clear with this idea of union find? Yes. Okay. Now final thing that we have to do is along with this information of connecting, how do we also remember what is the minimum road for any component? That is where I was saying we will take this idea along with parent array. We will take one more array called minimum road weight. That array will also be of size n plus 1. Initially, we will fill it with infinite value, very large value. And whenever you are joining two vertices, whenever you are joining 1 and 2, for 1, at root level, we will maintain the information, what is the minimum edge weight. So let's say 1 and 2 are connected with edge weight 7. If that was the first connection, then your min road of 1 will be what? What is the minimum edge that is connecting 1 to any other vertex so far? If 1 and 2 were connected with edge weight of 7. In this component, what is the minimum edge weight so far? Yeah, so far, if you have two vertices, 1 and 2, they are connected with edge weight of 7. What is the minimum edge weight so far? 7. Okay. Later on, let's say 2 gets connected to 3 and edge weight of that is 5. What will we do? We will find root of 3 as 1, root of 2 as 1. This weight is 5. We will go and update the minimum now to 5. So at root level, in union function, we just have to add one more parameter and we need to keep updating this array also. Yeah, is this idea making sense? Yeah. Okay. So quickly, if you really want, I can just show you the implementation of putting all the things together. Just one moment. Yeah. So if you really see, this is standard union find implementation. Number of sets I was not using. Yeah. So if you see, I just have it as a separate class. Take a parent array and take a rows array where I'm going to remember minimum row. Initially, what is this code doing? What is the constructor doing here? Yeah, so constructor is initializing. Parent as well as, yeah, it is initializing parent array as well as the rows, minimum rows for every root level. Okay. Then find root function we discussed just now. Okay, this is written a little more shorthand. If parent of I is equal to I, we are returning I. Otherwise, we are going to return find root. And there is one more slight optimization. This is called path compression. Even if you ignore that for now, that should be okay. This is find function. This is set union function. And this is minimum road. If I want to know what is the minimum road connecting U and V, I'm just taking a minimum of whoever is the root of U, whoever is the root of V. Now, if you see, all I was doing was for every edge, I was just inserting edges in the union find. And in the end, I'm just returning minimum road. Okay, guys, are we clear with the idea, implementation, logic? And can we say it is just use of recursion and array? There is no graph involved here. Yes. Okay, so this concludes our second last question.